Hey folks, today we're going to be talking about the continuous uniform distribution. So recall that if x is a continuous uniform variable, it is parameterized by the lower and upper endpoints a and b, respectively, in that interval. Okay, so the expected value can be found by integrating from negative infinity to positive infinity the PDF, which is just 1 over b minus a. We're going to integrate that, so the expected value is given by the integral of integrating that times x dx. Okay, so how does the story go? Well, the PDF is 0 unless we're in the interval a and b, right? So this is 0 unless we are integrating from a to b. Okay, but then this is pretty predictable, right? I can factor the constant out in front. The integral of x dx is just x squared over 2, evaluated from a and b. Okay, and then this is going to turn into, right, we're going to get a b squared minus an a squared divided by 2, right? Okay, but then this is a difference of 2 squares, so I can write that as b minus a times b plus a divided by b minus a times 2. And then since we're assuming a doesn't equal b, it's okay to cancel these out to get a final answer of a plus b over 2. So the expected value, or the average, is just simply the average of the two endpoints, which makes sense because if it is continuous and uniform, that means it takes on all the same values. So really, if you want to look at this as a discrete uniform, okay, where the number of discrete intervals goes to infinity, you can do it like that. So it's really a discrete interval where n, which is the number of blocks, goes to infinity, but you're still going to get the average nonetheless. Okay, my question is, you can derive the moment generating function by taking the expected value of, so find the moment generating function by taking the expected value of e to the xt. Okay, so that's going to equal the integral from negative infinity to positive infinity of e to the, tx times the 1 over b minus a dx. Okay, so it turns out that the moment generating function is given by the formula e to the bt minus e to the at, all divided by b minus a times t. So what the moment generating function does, if you recall, okay, so I'm going to give this a label, maybe m, which I'll label with an x, and it is a function of t, but I'm using x to label the random variable, okay? So in this case, the random variable x is continuous uniform. Okay, so the question is, how do we actually use the moment generating function in order to generate the moments? So remember that the first moment is just the expected value, and the second moment doesn't really have a special name, but the variance is the second moment minus the square of the first moment. So it might be a little helpful to know how to use this. Okay, so in order to find the first moment, so the first moment, which is also just the expected value, is the first derivative of the moment generating function, right? So it's the derivative evaluated at t equals 0. But the problem is, if you take the derivative of this function just straight up, you can imagine you might see a quotient rule here, and that's going to cause a t squared to be on the bottom. And when you plug in t equals 0, you're going to get a problem. Okay, so how can we be a little more clever in actually finding the first moment? So that is my question to you all. And my hint, because I want you to try this on your own, my hint to you, so hint, consider the definition of the derivative. Okay, so f prime of x at c is going to be the limit as x approaches c of f of x minus f of c all over x minus c. So I recommend using that. And then since we're dealing with a limit, now we can deal with any zeros on the denominator because we can factor that out, or we can use L'Hopital's rule. So that's hint number 2. So use L'Hopital. Okay, so I'm going to encourage you to pause the video and think about this. So this is the moment generating function. All you have to do is use the definition of the derivative in order to figure this out. Okay, and plug in t equals 0 after you're all done. All right, and we're back. So the moment generating function for a continuous uniform distribution is given right here. And recall that the definition of the derivative evaluated at a point, in this case 0, is going to be the limit as x approaches that point 0, okay, of the original function of t minus the function evaluated at the point in question, all divided by t minus 0. Okay, so the first part isn't so difficult, right? Okay, this is just the original function. This is just the moment generating function. So we're going to get that our first moment is the limit as x approaches 0. And our first component is just the e to the bt minus e to the at all over b minus a times t. The next component is the tricky one. The moment generating function itself evaluated at t equals 0, okay? But when you plug in t equals 0, you might have noticed that you get 0 over 0, which is undetermined. So the fact of the matter is this is actually not the correct moment generating function at all, because this is only true when t does not equal 0. When t does equal 0, the moment generating function has to be defined to be 1. That's the only way this works. Okay, so that being said, evaluated at 0 is defined to just be 1. And then we're dividing by t minus 0, which is just t. Okay? Now, since this is, well, you could probably approach this in a couple of different ways, but the way I'm going to approach it is I'm going to rewrite 1 in that special way. So this is, again, the limit as x approaches 0 of e to the bt minus e to the at all over b minus a times t minus b minus at divided by b minus at, right? This is nothing other than 1, and we're dividing all of that by t, all right? Which is going to equal the limit as x approaches 0 of e to the bt minus e to the at minus parentheses b minus a times t all over b minus a t squared, right, because of this t right here. Okay, now that looks pretty bad, to be honest, but we notice that since we reduced the problem, remember this is our answer, this is the first derivative of the moment generating function evaluated at t equals 0, so that's the expected value. So if we could just find that, we're done. Okay, and notice that all this is a limit where when you plug in x equals 0, or I'm sorry, this should be a t. I'm so bad about the t's. I've been awful about that, I apologize. Okay, so when you plug in t equals 0, you'll get 1 minus 1 minus 0, which is 0. So you get 0 divided by, of course, 0. So this is a prime candidate for L'Hopital's rule. You might have to use it a couple of times. So the symbol for L'Hopital, people usually write an L with an apostrophe. So to evaluate this, we just take the derivative of the top. So this is equal to the limit as t approaches 0 of the derivative of the top. Okay, this is a linear term, so we just pick up the b minus a. Now the derivative of the bottom is, we can factor this constant out, and then we just get the 2t. Okay, so I'm going to change colors. We're going to use L'Hopital's rule one more time. You'll notice that when we use L'Hopital's rule and we take the derivative of the top and the bottom separately, Well, this just goes away because it's a constant, and we get b squared b squared e to the bt minus a squared e to the at, all divided by, and then this is just a constant, so its derivative is 1, and we just pick up the 2 times b minus a. Hopefully you can see where we're going from here. We can now plug in the t equals 0 to get that this is now equal to b squared, e to the 0 is 1, minus a squared, e to the 0 is still 1, all divided by 2 times b minus a. We still have a difference of 2 squares, and we're left with our final answer of our expected value.